Okay, so everything seems to be ready. Are you ready, Simon?
I am ready.
So thanks everyone for joining us today. Sorry again for the glitch. The talk is at 5 p.m. as you can see, as usual. There was a glitch in some of the emails. Thanks for joining despite this glitch. I guess everyone here knows the rules, but just in case, if you want to ask a question, you have to type it in the Q&A box, and we'll try to unmute your mic. In case you don't have a mic, let me know when you ask a question, and I will read the question out loud. Otherwise, you should be able to speak, and I will let you know when you can ask your question. Okay. So without further ado, it's my pleasure to introduce my friend and colleague Simon Barthelmé from Grenoble, GIPSA Lab. Simon works on many exciting things, including kernels and machine learning, statistics, applied statistics, neuroscience. He did his PhD on human vision, and he's interested in many things. So your turn, Simon. I give you the floor.
Thanks a lot, Nicolas. Thanks a lot for inviting me. I'm going to show some work that was done first with Konstantin Mitrovic, who's actually done work on this, like the really difficult cases, the multivariate cases. It's his work, not mine. So hopefully I will do it justice. And more recently, we started working on applications of our results with Nicolas Tremblay and Pierre-Olivier Amblard, who are with me at GIPSA Lab. Constantin is at Cran in Nancy, France. Okay. To give you a bit of motivation for what I'm going to talk about, as we all know, kernel methods are pretty much central to modern computational statistics, and you find them under the form of Gaussian processes, support vector machines, spectral clustering, and so on. And of course, because they're central, they've been studied a lot. However, in most cases, these theoretical studies, they focus on large N asyntheses. So you assume that you have more and more data coming in, and then you look at what happens to the kernel method in that limit. Is it consistent? How does the posterior shrink, and so on? What I'm going to show here is a theoretical study of kernel methods, but it's not one that relies on large N asynthetics. It's a fixed sample limit that works rather differently. So instead of assuming that the data is going to become infinite, I'm just going to let one of the hyperparameters of the kernel function go to 0. Application to Gaussian process regression, where we'll see that in this limit, we can relate Gaussian process regression to well-known methods like polynomial regression. Okay, so to fixed notation, we're looking for the first part of the talk at kernel matrices, and their spectral properties. So we are given a set of n locations. So these are where our measurements are going to happen. For example, if we use DP regression, but here very generally it's just measurements. So it's a bunch of points, endpoints, for example, on the line or in the square, or indeed in any subset of R to the power D. So the kernel matrix is an n times n matrix with each entry given by a kernel function, so k of xi and xj. I'm not going to look at all possible kernel matrices. Here we think of kernel matrices as similarity functions. So so the similarity is a decreasing function of the distance between points. So here I'm going to assume that the kernel matrices are formed with kernel functions that are so-called RBF, radial basis functions, which just means that the k of xy just depends on the distance between x and y, the Euclidean distance. Okay. Well-known example is the most famous one is the so-called Gaussian or squared exponential kernel function, which is just exponential of minus epsilon times the distance squared. A rather different kernel function, although it looks on the surface quite similar, is the so-called exponential kernel, where instead of having the distance squared, the distance. So exponential of minus epsilon distance from x to y. And here the parameter that I called epsilon, for reasons that are going to be obvious in a second, is an inverse scale parameter. So it tells you at which rate the kernel function goes to 0, so the similarity goes to 0 as the distance rises. And so that's an inverse scale parameter. And what I'm going to look at is what happens to the kernel matrix as epsilon goes to 0. So that means the scale goes to infinity. Okay. The reason I give these two examples of kernel functions is because they have strikingly different behaviors in the flat limit. Okay, so just to be a bit more graphical, here's an illustration of the squared exponential kernel function. So here you center at certain point x in dimension 1, and you look at the kernel function. Of course, it's a bell curve, and as you the smallest width is given by here in this plot epsilon equals 3, and then as you decrease epsilon, the becomes flat, and that's the reason. Now, the first reaction for most people when they hear this limit is to think that it makes no sense whatsoever, and that's quite understandable because as epsilon goes to 0, the basis function, so the kernel function becomes flat, and so the kernel matrix tends to just a constant value. Every entry is the same constant value. Sounds like a very interesting limit. So actually, this limit is much more interesting than it sounds, and there's several ways of seeing that. And I think the historically most important one came from a result in approximation theory by Driscoll and Thornburg in 2000. So this is a very influential result in approximation theory. Driscoll and Thornburg had a look at what happens to Gaussian radial basis function interpolation as epsilon goes to 0. So to be more precise, here's what they did. So RBF interpolation is a special case of Gaussian process regression action. Gaussian process regression is essentially when you assume they have no observation noise. But from a more classical viewpoint, not Bayesian one, what you want to do is interpolate a function given measurements at n different locations, and you want to know what's in between. So you assume that the function can be written in a span of a certain number of basis functions associated with the n observations. And here, so you just say in RBF interpolation, the basis functions are just the kernel functions evaluated at each measured location. Okay, so you just do a weighted sum of these kernel functions, and this is your RBF interpolation. Very classical way of solving the interpolation problem is to, so instead of using basis functions that are localized at each measurement location, we just use a basis of polynomials. So here I've written this interpolant in terms of the monomial basis. So it's just you take x to the power 0, x to the power 1, x to the power 2, and so on. And you need n bases to go to up to x to n minus 1. Take a weighted combination of that, and this gives you radial basis functions. Okay, so visually, what does it do? Well, here's an illustration again of a interpolation with I think 10 locations here. So in black, I have radial basis function interpolation with a Gaussian, so with a value of epsilon set to 15, because of course what result you get depends on how wide the basis functions are. So this is for epsilon 15, and I'm going to reduce epsilon 10, then 5.6, then 0.9, and then you see that the black curve converges to the dotted red curve. And now, what is the dotted red curve? Well, the dotted red curve is just the polynomial interpolant. Okay, so that's essentially the result that Driscoll and Thornburg obtained in 2002. They proved it formally. If you have in dimension 1 Gaussian RBF interpolant and you let it become flat, then it converges to a interpolant. And this was very surprising back then, because if you have basis functions that become flat, it doesn't sound like the interpolant is going to exist. because you can't interpolate a function with just flat basis functions. So it's very surprising that it does. And not only does it exist, but it tends to
breaking up.
something that's well known in maths. So what I'm going to show next is just empirical behavior of
Simon?
Yes.
The last 20 seconds, I could not hear a thing. I think it was frozen for me. Is it the case for you, David, as well?
No, I think it must have been Simon's end.
Oh yeah, somebody called me on the phone, and I'm sharing my. Okay, my bad.
Could you come back a little bit? Yeah, sorry.
Yes. Okay. So what I showed just before, a first hint that something's going on that's interesting. The Driscoll-Informal bank result. So here's the second hint. The second hint is looking at the empirical behavior of the eigenvalues of kernel matrices in the flat limit. So here's empirical data. I mean, it's just a simulation, but I picked 20 plane. So these are my blue dots, and then I formed a kernel matrix using the Gaussian kernel. Okay, so here's a heat map of the kernel matrix, and so gold values are high values of the kernel function, and black are low values. And as you reduce epsilon, unsurprisingly, that every value in the kernel matrix tends to 1. However, if we look at the value of the eigenvalues, we see some interesting behavior. So this is all the eigenvalues sorted, okay, and plotted as a function of their index. So this is from the highest eigenvalue to lowest eigenvalue for epsilon 2. Next, I reduce epsilon, and as I reduce epsilon, we can see some pattern emerging here, and the pattern looks like a slanted staircase. If you see this is the first eigenvalue, then the next 2, then the next 3, then the next 4, then the next 5. There's an actually after 5, there's I have 20 points, so that's all I have room for. But after 5 eigenvalues that are grouped together, there's another group of 6, and if I had more points, I had another group of 7 eigenvalues, and so on and so forth. So this must there's something going on here. So what is it? Well, this was first proved by Shabak in 2005 in passing. He did not think this was particularly noteworthy, but we think it is. There's some kind of slanted staircase pattern that appears. And it appears because the first eigenvalue is of constant order in epsilon. So it doesn't go to 0 as epsilon goes to 0. Then the next 2 eigenvalues are of order epsilon squared. This block of eigenvalues goes to 0 as epsilon squared. Then the next block of eigenvalues, they go to 0 as epsilon to the power of 4. And then the next after that, epsilon 6, and so on and so forth. So that's the spectral behavior for eigenvalues of Gaussian kernels. And it's a second, something's interesting going on in the flat limit. So our objective when we started this was to characterize the eigenvectors and the eigenvalues of kernel matrices in the flat limit. So we wanted to get not just the order of the eigenvalue, but its approximate value, if you like, the coefficient that comes along with the order. There's a bunch of other stuff we have from these results as well, determinants, regularization, but it's mostly the eigenvectors and eigenvalues that are interesting when you look at the limiting behavior of kernel methods. So I just showed the pattern of eigenvalues for the Gaussian kernel, and I said at the beginning of the talk that Matern type kernels, for example, the exponential kernel, behave quite differently. So let's have a look. So this is now the exponential kernel. Again, I'm going to go from epsilon 2 to epsilon very small, And what you see is instead of having several different blocks, you only get two. I know this looks like a block, but it's not, because the gap is less than an order of epsilon. It's related to, but it's the same points. And instead of having a block going with epsilon to the power 0, then epsilon 2, epsilon 4, and so on, the behavior is quite different. And we can, using our results on the limits, we know what it is. There's only two, and the first block is of order epsilon 0, so it doesn't go to 0 as epsilon goes to 0. And the second block is of order O of epsilon. Okay, so this is quite different from the Gaussian kernel. It gives you a matrix that's much better behaved numerically, because it is orders of magnitude better than the Gaussian kernel. So what's going on is actually related to the regularity of the kernel function. So exponential of minus epsilon x minus y is not differentiable in x and y equals y. It's a question of differentiability. I can't go too deeply into that, but if you look at, for example, the exponential kernel as a covariance of a Gaussian process, you get a Gaussian process that's not differentiable. It's continuous, but it's not differentiable. Whereas the Gaussian process that comes from a squared exponential kernel is infinitely differentiable. And the behavior of the eigenvalues. So, okay, I'm going to skip this in the interest of time. But if you increase the order of your kernel function, so increase its regularity, you get a behavior that's sort of in between these two things, the exponential kernel and the squared exponential kernel. So you start seeing more blocks of eigenvalues. So formally, what's going on? Well, the main result is tries to characterize the eigenvalues and the eigenvectors of a kernel matrix as epsilon goes to 0. I'm not going to give the full result here because it's too complicated, and there's subtleties and corner cases. But if you keep things to unidimensional cases, so you imagine that the kernel matrix is just describes points in the on the line, then things are more readable. So let's have a look. So this is d equals 1, so we're on the line, and the result says eigenvalues of Gaussian kernels, for example, so infinitely smooth kernels. Each eigenvalue can be written as follows. It's epsilon to the power of 2i minus 1. So I've sorted my eigenvalues from largest to smallest. Epsilon to the power of 2i minus 1. So this is how fast it goes to 0. Then lambda I tilde. And lambda I tilde is the coefficient that we can extract to get an approximation. And we know how to compute lambda I tilde. I can't give you the formula here, but it's easy to compute. So in dimension 1, we know exactly the speed at which each eigenvalue goes to 0, and we know we know the coefficient behind. So just to illustrate this a bit, again on an empirical example, what you see here is a plot of on the x-axis it's epsilon, on the y-axis it's the eigenvalues, and here it's the top eigenvalue of a kernel matrix. Okay. So you see that it doesn't go to 0. Epsilon goes to 0. This is the next largest eigenvalue of a kernel matrix, and we see that it goes to 0 as epsilon. And I want to stress that this is a log-log plot. Otherwise, on a normal plot, of course, this would go to 0 extremely fast. The third eigenvalue goes to 0 even faster. The fourth eigenvalue, and so on. The dotted red lines here are the asymptotic approximations you obtain from the formula I just gave on the preceding slides. So it's the order times the lambda I tilde coefficient that you can get from our theorems. Okay. So the interpretation is as follows. As 1 goes to 0, every eigenvalue goes to 0 except for the top one. So this, you get a matrix that's horribly badly conditioned. And each successive eigenvalue goes to 0 faster than the preceding one. So every eigengap increases. Okay, so, and that determines a lot of the behavior of kernel methods in the flat limit. So that's for eigenvalues. Now we can look at eigenvectors as well. And what's going on with the eigenvectors is rather surprising. So if the kernel is completely smooth, so that's again Gaussian case, the eigenvectors are orthogonal polynomials. Specifically, they're constructed as follows. If you I'm defining a set of vectors of v0 to vn minus 1, where vj is the locations x1 to xn to the power j. Okay, so we start with x1 to xn to the power 0, so that's just a constant vector. Then the next order is x1 to xn, then it's x1 to x1, h1 squared, and so on. So these are my monomials evaluations. Now you apply the Gram-Schmidt process. Okay, starting with order 0 and going to order n minus 1. So to these vectors v0, v1, and so on. And so you get q0, q1, and so on. So these are orthonormal eigenvectors. Orthonormal vectors. And the surprising result is that every eigenvector of k of epsilon is one of these orthonormal orthonormal polynomials. Okay, so there's a very simple characterization of eigenvectors of kernel matrices in that limit. They're just orthogonal polynomials constructed using the usual method, Gram-Schmidt. It becomes a bit more complicated in the multivariate case, but in 1D it's very, very simple. Okay, so here's empirical example again. Same data, 2 slides before. Now we look at eigenvectors as epsilon goes to 0. So this is in successive values of blue here. The first eigenvector, second eigenvector, third and fourth. And the limit is in red. And because it's orthogonal polynomials, what you recognize here is a function, then a linear function, then a quadratic, and then a quartic. Okay, and you see the eigenvectors of the kernel matrix converging to these orthonormal eigenvectors. Orthonormal polynomials, sorry. Keep mixing that up. Okay, so that's for a kernel that's infinitely smooth like the Gaussian. What happens if it's not a Gaussian, for example? What happens if it's a Matern kernel? Well, the whole story is too long to tell, but here's a summary of what's going on for the exponential kernel, which is my running example. The limiting eigenvectors, in this case, are just the constant vector that's associated with the eigenvalue that's of constant order, just like the Gaussian, but all the other eigenvectors are different. And the eigenvectors of a very interesting matrix, which is the distance matrix, okay, which is just the Euclidean distance between points, with the constant vector projected out. So this says n minus 1 eigenvectors, and these are the limiting eigenvectors of the Matern kernel of smallest order, so the exponential kernel. All right. Now, why is this matrix interesting? Well, it turns out to be related to piecewise linear spines. Okay, so this gives you a basis essentially for the piecewise. So again, we can get the eigenvalues, where in black we have empirical eigenvalues. You see that they're all going to, so except for one, they're all going to 0, but at the same rate. And we can capture the rate and intercept on the log. And we can also capture the limiting eigenvectors. So this time it's not so you get a constant function as the first eigenvector, but the rest of the eigenvectors are not polynomials. So this is not, for example, this is not linear, and this is not quadratic. They're different eigenvectors, and they're related to linear spline. Okay, so a summary for this part. We know that the eigenvalues of kernel matrices exhibit certain mathematical patterns, even though the limit is a constant matrix. And this is the reason this happens is we have a singular perturbation problem, meaning that the limit of the eigenvectors is not the eigenvectors of the limit. So that makes it quite remarkable, but also very hard to study. The most theoretical results we used came from a book by Cato on singular perturbation of linear operators. The limit, so more practically speaking, the limit depends on the regularity of the kernel function. If you have a kernel function that's highly regular like the Gaussian, you do different behavior than from a method of low. Okay, so that's it for kernel matrices. Now let's look at an application. Are there questions so far?
Just to be sure, Simon, I understand. I mean, since you say that the limit of eigenvectors, not the eigenvectors of the limit, that means in practice, if I take epsilon very small, I get completely different result that if I take epsilon equals 0.
Yes.
And epsilon equals 0 will give you the constant matrix.
Exactly. So epsilon equals 0, your kernel matrix is just 1, transpose. So it has a single non-vector. But at any value of epsilon you get a whole set of eigenvectors because the matrix is actually invertible for any epsilon larger than 0.
Okay.
So that's the subtle behavior here, and what makes it difficult to study.
All right, thank you.
And can we use like standard intuition? Does it, like, if it's nearly all ones, does that mean every point is quite strongly correlated with every other point? Can we think of it that way? Or?
Yeah, exactly. So as an approximation, the flat limit applies as soon as the width of the kernel is large enough to cover the whole data set. In some sense. So it applies for matrices, kernel matrices that are non-sparse. So if everybody essentially can see everybody else, then you're close to the flat limit.
Simon, you mentioned the other limit when you take the noise level to 0.
Yes.
What's the connection with this? I didn't get it.
Okay, so in Gaussian process regression, you usually have non-zero noise because it's very, except in like modeling of computer experiments, it's very rare that you assume that the actual function is what you observe. However, if you take the limits where the observation noise is 0, then expectation of the Gaussian process has to go through the points that you measured.
Yes.
And that makes it an interpolant.
Right.
It turns out to be the same as something that was defined much earlier, which is an RBF interpolant, a radial basis function interpolant. And so that's an object that's been studied in information theory.
Okay, but that's still a different limit from what you get, right?
I'm sorry?
That gives you a different limit.
It's an unrelated limit.
It's unrelated. Okay, that's what. Okay, there's no connection between the two.
There's no connection. It's just you can think of it as a special case of Gaussian process regression.
All right. Okay. Thank you.
Okay, so I'm just going to look now at Gaussian process, and I'm going to define some notation first, and then I'll very, very roughly sketch what Gaussian process regression is and how it works, because I don't have much time. So we're going to think of Gaussian processes as distributions over functions. And they're very useful in Bayesian stats as prior distributions over functions that allow you to express the fact that, that, for example, a classification function that you don't have a specific parametric form for, but you can assume that it's, for example, smooth, or that it decays at a certain speed, or so on. So we think of Gaussian processes as random functions. And if you observe a Gaussian process at a finite set of locations, then you get a random vector. And what makes it a Gaussian process is that this random vector has a multivariate Gaussian distribution. Okay, so here's an example of sampling from a Gaussian process. And here in this case, I'm going to use it as a prior. I'm going to assume that there's some kind of relationship between x and y that's described by a function that I haven't observed yet. And I assume that this function is smooth. Okay, so I get different samples. So that these are samples from a Gaussian process. And I can modify the prior by tuning the hyperparameters. So here I've increased epsilon. And I get different samples. For example, these tend to evolve a bit faster than previously. Okay. Now, this is my prior. And I can also condition on some observations. So here, the blue dots are observations from my unobserved function plus some noise. So these are the noisy observations. And the curves you see in different colors, these are samples from the posterior distribution of the Gaussian process. So we condition the Gaussian process on the observations. And this gives us a distribution over functions, so random functions, but this time they're constrained by the data. So that's Gaussian process regression in a word. Instead of usually summarizing it from samples, what we do is we take the mean at every location, and then 2 times the standard deviation at every location, and that's and our measure of uncertainty. All right. So if you know Gaussian processes, you know that there's one central matrix that we need, and it's this matrix. It's just the covariance of the Gaussian process evaluated at the sample locations. So here we have, again, a kernel matrix, because the covariance function needs to be positive definite, and it takes this covariance matrix takes the form of a kernel. And all the important computations are going to involve the matrix K, which is n times n if you have n locations. And it's the same as what we studied before. If you want to like a brief sketch of what's going on formally in Gaussian process regression, we assume the following model. We assume that f, which is our latent function, is sampled from a Gaussian process with mean 0 and covariance function kappa. And the observations, so the yi's, are some conditional on f, the latent function, are just Gaussian observations with variance sigma squared. And now a miracle happens. The posterior process, conditional on y, is still a Gaussian process. So that's conjugacy. And that's what makes the theory elegant in the Gaussian case. Posterior process is still a Gaussian process. Okay, so how do we get our fit? Well, we get our fit from the expectation of the posterior process, and it's very easy linear algebra. So for example, the expectation of the Gaussian process given the data at point x is just going to be given by something involving the matrix K, then something involving the relationship of x to the sampled points, x1 to xn. Okay, but it's just one of the observations y. Now, our goal here is going to apply the flat limits in this case and figure out what's going on with these fits and standard deviations, actually, as we let epsilon go to 0 in the flat limit. And we'll see that a connection to polynomial regression appears. So polynomial regression, well, we've just saw polynomial interpolation, which is also a special case of polynomial regression, which is very easy to explain. It's just you assume that you have observations yi, then you want to regress them on a set of basis functions which are given by the monomials up to order m. Okay, so you just, it's the coefficients beta for the monomials that minimize this quadratic form. And if you can read R, this is as basic as it gets. You're just saying, I want to regress y on the polynomial of order up to m. So that's polynomial regression. And we're almost ready to characterize the behavior of Gaussian process regression in the flat limits. There's just one missing element. There's actually 2 hyperparameters typically in the covariance function. So one of them is epsilon, which is our scale parameter, inverse scale parameter. I call it here gamma, and gamma gives you the height of the kernel function. So epsilon we think of as width, and gamma we think of as height. In most applications, what you do is you set epsilon and gamma both using some kind of hyperparameter selection, for example, leave one out, or you integrate over it using standard Bayesian methods. Okay, so why is that important? Well, it's important because of the following observation. If you think of Gaussian process priors, and so let's to 0, it sounds like you're not going to get something very interesting, right? Because as you let epsilon go to 0, then every location is heavily correlated with every other location, and the samples from the prior are flat. So it sounds like all we're going to do is recover a fit that is flat and uninteresting. But there's actually something subtle going on. It's true, but only if you let gamma be constant as a function of epsilon squared. No, sorry, of epsilon. So it turns out that's not what you want to do. What you want to do is you let the height of your kernel function, let it increase as the width increases. Okay, so to understand that, we need to look at a very simple notion on this theory of linear smoothers, and that's the notion of degrees of freedom. So the degrees of freedom of a fit, they tell you essentially the dimensionality of the space your data is projected to. So let me describe it. You have an estimate f hat of your latent functions at the sample location. And this is given by, it's just a linear function of the observations y, and it's given by this matrix k times k plus sigma squared I inverse. And this matrix that ties the data to the fit is called the smoother matrix. Now, the degrees of freedom of the smoother matrix tells you how highly you penalized. Okay, so if you have low degrees of freedom, that means that essentially projecting the data to a very low dimensional space. So the fit is very penalized. If you have close to n degrees of freedom, you just recover your data, and the fit is completely unpenalized. Okay, so high degrees of freedom, less penalty. And now we can plot the degrees of freedom as a function of epsilon and gamma. So this you should read as inverse width. So here the width is going to infinity, and this is height. So height is going to infinity here. Okay, and what I'm plotting here are the contours of the degrees of freedom of the smoother for a specific data set. So you see that if you cut along a vertical line here, so as you increase gamma, the color goes from black to orange, and so that means that you increase the degrees of freedom. Now, if you cut across, so this is epsilon going from epsilon 10 to epsilon going to 0, and you see that you decrease very fast the degrees of freedom. So if you want to keep a fit that has a fixed degrees of freedom, you have to go along a contour line. And the theory says that these contours are actually linear in log-log space. You can study the asymptotics of that. Okay, so we know how to move along a contour. As epsilon goes to 0, we can keep the degrees of freedom constant. So this is how you should think of the limit, the flat limit of Gaussian processes. In order for the limit to be reasonable, we want to keep the freedom constant as epsilon goes to 0. So that means increasing gamma, increasing the height of the kernel functions. So I'm going to insist on this because it's actually significant. These contour lines that we saw here, where the degrees of freedom are constant, we have a very ugly word. We call them isofreedom lines. And these isofreedom lines also turn up in hyperparameter selection. Okay, so this is an example of a data set. So these are noisy observations of just a sine or cosine. I plot here 3 different hyperparameter criteria as a function of epsilon and gamma. So this is what you would use to set epsilon and gamma. And for example, let's look at leave one out here. So black is good and yellow is bad. So leave one out would tell you to pick a value of epsilon and gamma along here. But you see that it's not viable. Because essentially what it says is that as epsilon becomes small, then instead of having two hyperparameters, we just have one. So this gives you a valley, a very long valley. Essentially all you have, the only thing you need to pick is the number of degrees of freedom. And then anything along the line here is non-identifiable. Okay, and you see the same behavior for sure. So that's Stein's criterion and a variance of leave one out here. It's not the case for the marginal unlikelihood for the case for reasons I can't really get into. But for predictive criteria like Shor and leave one out, you get these values where any pair of epsilon and gamma along these lines is essentially the same. Okay, so I now have all the elements I need to state my results, but I can't state it formally because there's too much notation to use, and I think it's more understandable stated informally. So informally, here's a result. If you have an infinitely smooth kernel, so the Gaussian, for example, a Gaussian process fit is going to behave essentially like a polynomial regression with the same degrees of freedom in the limit. To take epsilon to 0, you're doing the same as a polynomial regression with the same degrees of freedom. So, and the degrees of freedom in a polynomial regression is essentially how many monomials you pick. Now, it's another interesting. It's not just the fit that converges in the flat limit. It's also the predictive variances. Okay, so the variance of a Gaussian process regression also matches the variance of a polynomial regression as epsilon goes to 0. And in order to illustrate this, I'm going to show an animation. Okay,
Simon,
so, yes.
we have a question from an anonymous attendee.
Okay.
So I don't know if I can open the mic of someone anonymous. Let me see. Okay, I don't know. I'm not able to do that.
Okay. Can you...
But let me read the question. Yes. Why plot epsilon and gamma if you have chosen other parameters? Will it not capture the fit?
Okay, so here okay, so the way leave one out, for example, so the way you'd apply leave one out in practice is you'd start from some value of epsilon and gamma, and then you let some optimization function find a local minimum. What I'm plotting here is essentially the surface that corresponds to the well, the optimization, the cost surface for leave one out function of epsilon and gamma. And what it shows you is that at least in this region, there's no unique minimum. There's just valleys and infinitely long valleys. So these values, you're not going to reach them in practice because of numerical issues, but theoretically they exist. Theoretically, you can, the problem is that empirically, if you have to invert kernel matrices, and doing this as epsilon becomes small, it's difficult if you do it in a naive way. For example, if you leave a nugget term, these values completely disappear for artificial reasons. But theoretically, they are there. So there's, if you could compute this accurately, it could be that the actual optimum is for epsilon going to 0. I hope that explains a bit.
Is the predictive distribution on different points in the valley different? So
No, it's the same.
It's the same.
The distributions all tend to the same
for a new point. So in a sense, it doesn't matter?
No. So as you run along this valley, nothing changes. I mean, you tend to a limit, essentially, but that's all that's going on. However, I mean, how fast you reach that limit, that depends a lot on the geography, on the geometry of the data. I haven't really talked about it, but for example, if you have like really wide outliers that are very, very far away, you're not going to reach the limits. Kernel functions reach these outliers, which might take a lot of time. So that might be for epsilon very, very small. But if you have distributed in a compact domain, then you can reach the limit quite fast. It's something we don't really understand yet. Like geometries make the flat limit happen fast versus slow. It's we don't really have the tools yet.
I think you can proceed, Simon, if you want to.
Okay. All right. So what I'm showing now is again made up data, but this time we have a number of things going on. We have 4 black curves, which correspond to different polynomial fits. So the points are observations. Again, they're noisy, and it's a sine. And the black, it's the polynomial fit of degree 0, so it's just a constant function. Then we have a linear fit here. So that's degree 1. Degree 2, we have a quadratic function. And then at degree 3, we have a quartic. So these are polynomial fits. Now, the blue line corresponds to a Gaussian process fit. Okay, so I leave epsilon fixed, and all I change is the degrees of freedom. So essentially, I change gamma. So epsilon is fixed here. It's equals 0.2, but it's fixed. So what's going to change during the course of this animation is the value of gamma. And what you see is the Gaussian fit essentially cycling through the different polynomial fits. Okay, so here it's almost quadratic, and then next is going to go between quadratic and quartic, and we're almost at quartic here, and then we cycle again, flat to linear, linear to quadratic, quadratic to quartic, and so on. So that's what happens as you increase the degrees of freedom with epsilon fixed, and this is the way that should happen. All right. And so this was for infinitely smooth kernels. For exponential and other return kernels, again, the story is a bit more complicated. I apologize, but I can only sketch it. Depending on the degrees of freedom and the kernel, the Gaussian process model is going to converge either to polynomial regression if you have low degrees of freedom, or if you have a higher number of degrees of freedom, it's going to converge to a polyharmonic spline, which I don't really have the time to really properly introduce. But a polyharmonic spline is one of the extensions of splines to multispace, because in 1D, a spline is just something that's polynomial between breakpoints. It's not immediate how to extend this to larger dimensions. So there's several different possible extensions, and one of them is polyharmonic splines. And it turns out that polyharmonic splines actually the behavior of Gaussian as epsilon goes to 0. Okay, so in conclusion, from a theoretical viewpoint, we have tight links between kernel methods and, on the one hand, and orthogonal polynomials and splines, which show up in different places. We can show that Gaussian process regression tends to a polynomial regression or polyharmonic spline regression. Now, we have most of this is in a very complicated SciMax paper with very complicated proofs. And it turned out that for that paper, we reinvented a lot of wheels. And we're now in the process of simplifying this mess. So hopefully in a few weeks, we'll have an updated paper with much simpler proofs, I hope. Something I haven't talked about, we have another paper that examines the flat limits of determinable point processes, which also has interesting things going on. So that's from a theory point of view. And no, I guess a lot of you would be interested in practical aspects as well. And that's something we haven't investigated enough. So what I can tell you so far is that as a practical approximation, the flat limit sometimes works very well and sometimes poorly. So I mean, it always works in the sense that if epsilon is small enough, you'll get there, but how fast you get there varies. And it varies according to the geometry of the data points and the Taylor expansion of the kernel in ways that I don't really know how to handle yet. So there's more work needed there. No, there's something that should help, which is that the flat limit always applies in some sense to the diagonal blocks of a kernel matrix, because make the diagonal block small enough, then you have an area in the matrix where every point is close to every other point. And so over that block, the kernel function is flat. So you can apply the kernel matrix, that limit sort of blockwise. And then there should be a way of using far field approximations to deal with the blocks that are off diagonal in the kernel matrix. But we're looking into that as well. No, one last thing that I think is important from a practical point of view. Polyharmonic splines and polynomial basis functions have something interesting, which is that they're epsilon free. You don't need a scale parameter, and so that's one less thing to worry about when you're doing fits. And the fact that they occur as a limit of Gaussian processes, I think should count in their favor, especially for polyharmonic splines, which have nice properties. So you can think of them as non-parametric models, polyharmonic splines, that do not have the epsilon parameter and also occur naturally as a limit of Gaussian processes that should make them interesting, I think, in practice.
If you're in
yes.
Sorry, a quick question. If you're in multiple dimensions, like it would seem you'd have an epsilon for each dimension. It seems too good to be true to get rid of like both of them. Is that?
Okay. So yeah, that's a good point. In standard Gaussian process regression, okay. So if you assume that your covariance matrix does not depend, the covariance function does not depend on the dimension, then you have a single epsilon parameter. If you have multiple hyperparameters, each according to okay. Essentially, you can deal with multiple epsilons by just rescaling the data. That's all I can say. If you're worried about this, you just rescale the data. You can let all the epsilons go to 0. In a way, it's hard to explain. I'm sorry. However, there's a case which the theory doesn't really deal with, which is where certain dimensions may be dropped over the course of fitting the Gaussian process model. So that's a popular thing in machine learning, where you have a lot of dimensions, a lot of features, and you want to drop some of them. And that's not something the deals with yet. The other case you can sort of deal with by just rescaling the data. That makes sense.
What are relevance determination stuff?
Exactly, the automatic relevance determination we can't really deal with. I don't know I don't know what to say about it really in this framework, but non-isotropic covariance functions that can be dealt with using rescaling the data.
Simon, we have a question from Adrien Corenflo. I think Adrien does not have a mic, so I will read his question. GP regression with stationary kernels can be represented by state space models via some spectral decomposition, essentially an SDE with some noisy observation.
Yes.
Have you thought of your result in these terms?
Okay, yes. Thank you. All right. I have. It's complicated. So in dimension 1, there's something interesting that happens, which is if you take for example, the exponential kernel and the flat limit, it becomes a regression on linear splines. so piecewise linear functions, and it has a certain Markov property, and it's related to the Laplace operator. So you can sort of tie in the state space stuff, the stochastic PD stuff, and the flat limits, and they sort of and they turn out to be very tightly related. So that's in dimension 1 because you get like some kind of Markov property. You get a relation to the Laplace operator, sorry, harmonic functions, and so on. In dimension 2, it's not so tidy because you get a fractional relation in there, and I don't know how to deal with it, to be honest. So it's a direction, and there's not much I can say beyond dimension 1.
Okay, thanks. We don't have any other question for them now. Anyone wants to ask a question? Were you finished, Simon, by the way?
Yeah,
you were done, right?
Yeah, sorry. I'm done. Yeah. The references are here. Thank you.
I just wanted to ask something. So in the multivariate case, splines are difficult. Would you recommend doing GP regression with a very small epsilon in order to do spline in a more would it give us a convenient way to do a spline in a high dimension in some sense?
So polyhomines are not so difficult.
They are not?
No.
Okay.
They still have n-cube cost if you do it naively. So you don't get rid of the n-cube problem, which you do in dimension 1. So in dimension 1, spline is essentially order of n.
Yeah.
Polyharmonic spline, sadly, are cube in dimension 2, although there are some low rank approximations. But like the numerics are not there yet, I think, for polyharmonic splines and for large data sets. However, if you have data on the orders, it's you can just eat the n-cube cost, then it's fine. They're interesting models. They don't deal very well with strong outliers. That's something to think about. But other than that, they're nice models.
So if you're happy with the n-cube cost, you can do either Gaussian process regression with small epsilon or this kind of spline. You will get the same result for the same cost, essentially.
Yeah.
Okay.
But you get rid of the hyperparameter.
Yes. Okay. And I think Adrien is back asking or saying, essentially in dimension 1, you get an SDE representation of polynomial regression. I think it's a statement.
Possibly. that sounds likely.
That was a question, actually.
Okay. Oh, it's a question. Okay.
Yeah, so the question mark arrived later. The second name.
Okay, so let me think about it. I think I agree with it, but I need to think about it a bit, to be honest. It sounds like something you get.
In the meantime, we also have a question from Olasumbo. Olasumbo, let me try to see if I can let you speak. No, I don't have any right to unmute people, I think. David, do you have a right to unmute people, or do you have a permission maybe?
Yes.
For Olasumbo Banjoko?
That's not me, like David, you missed.
Okay, it should be good.
I actually could speak, by the way, Nicola.
Okay, sorry.
No worries.
Oh, I thought because you said, okay, in your first email at the beginning of your talk, I thought you said you could not talk, but sorry. All right. Ask to unmute. Okay.
Hi.
Can you talk? Yeah, okay. Please ask your question.
Yeah, so basically, I'm checking if what method is more applicable, seeing that like we have a linear fit and a quadratic fit, because the question from the formula where you had k into bracket k plus
Yes.
gamma raised to the power of epsilon, that's a linear equation. But when we had the plotting, you know, we had a straight plotting, which was a straight line, and then we had a quadratic. So I'm wondering, what's the best method? Like, what's the best, where would I, if I had to apply this?
What are we talking about?
I'm talking about yes, the
Okay.
fitting
Well,
of the points
yes.
from to the formula. So if I had to make a guess, if I want to do like a research and I had to apply this formula, what's the best? Is it in parametric or non-parametric? Like, what's the best application? I'm just trying to figure out.
Should you go polynomials or non-parametric methods?
Yeah.
It's a difficult question. So it really depends on the dimension. And on the geometry of the data. All right, so in dimension 1, for example, polynomials have the advantage of being computationally cheap. Ways of doing computations in less than n cube time. So in less than quadratic time, actually, in the order. However, they behave very well in the region, but they're known for being very bad at extrapolation because they have oscillatory behavior as you extrapolate. So they go towards minus or plus infinity, essentially. So you shouldn't trust a polynomial fit outside the range of your data. However, they can have very good practical performance. Empirically, they're quite cheap. So that's one advantage. Tend to be really good across the board for dimension 1. And they extrapolate a bit better because you control the boundary conditions. You can say outside the range of my data, essentially I can impose boundary conditions. So I can go to I can reset to 0, or I can have a 0 derivative and so on. So splines are more controllable and they have pretty good empirical behavior, and essentially they're linear as well. So they order of n. Okay, in higher dimensions, it becomes more complicated and depends on what you want to do, whether you're in a sort of spatial statistic kind of setting or if you're in a machine learning kind of setting. For machine learning, if you have high dimensions, there's other results coming from random matrix theory. For example, in my lab, there's Romain Couillet who works on that, which so these results say that in high dimensions, in certain cases, the eigen functions of kernel matrices are actually just like linear and quadratic basis functions for different reasons than what we have here in the flat limit. But again, you recover like linear and quadratic polynomials, so essentially parametric functions, because in high distances tend to converge to the mean distance. So for they've shown that for certain machine learning settings, you can get really good performance out of methods that are parametric in this sense. However, if you need to extrapolate much beyond the data, then parametric fits can be really bad. And a Gaussian process that sort of nicely goes back to 0 is a bit better. So you would at least need to treat extrapolation a bit differently than interpolation. But it's a whole topic.
Okay, I don't see any other question from the audience. So
basically, we're going to be able to do both.
yes, someone was speaking, no? Okay. So thanks a lot, Simon, for a very interesting talk.
Yeah.
We should have more GP talks, I think, in our seminar. It's a really cool topic. Thanks a lot, Simon, and see you in a minute. And on behalf of everyone in the audience, let me clap.
Thank you.
Goodbye, everyone. See you next talk. David devrait nous envoyer un nouveau lien pour...
Ok, super.